Okay, here's an example where we use friction. So I've got this beam. It's supported by a spool over here. Okay, it's 40 kilograms spool. We want to find the minimum force P that's applied to this cable, which is wrapped around the inner core of that spool. Okay, coefficient of static friction between B, which is at the top here, contacting the beam, and D, which is here contacting the ground. This one's 0.4, this one's 0.2. And I want to figure out the minimum force required to get motion. Okay, so we're going to start by drawing some free body diagrams. And we'll start with the beam. Okay, so I've got a pin over at A. I've got the 200 newtons right here. I've got the normal force at B, which is at the spool. And then I have a friction force at B. Okay, now I can sum the moments about A, which I will do right here, and the only thing I'll be able to solve for NB. Okay, so if I sum the moments about A, basically I have 3 times NB minus 2 times 200. That tells me that NB is 133 newtons. And again, this is true regardless of what's going on with the friction. Okay, the normal force at B is going to be 133 for this loading, based on that free body diagram. And this is really the only equation we need from this free body diagram. So now we'll draw of the spool, okay? Again, I've got NB, which I just solved, is 133, so I can go ahead and put that in there. And again, this is true regardless of what's going on with friction. Okay? I have the weight here, which is 40 kilograms times 9.8. Okay? I have this friction, which I had up here. Newton's third law tells me it's in the opposite direction. Okay? I have the force P that we're looking for. And then I have friction and normal force down here at D. Okay, so I've got normal force at D and friction. Now these frictions are going in the opposite direction of P, right? Because they're trying to oppose the motion. So I draw those two frictions in the opposite direction of the force P. Okay, and notice I just call them F at this point. I don't do anything further with them. So now I'm going to go ahead and write my equilibrium equation. So I have the sum of the forces in the x. I have P minus my 2 frictions in the x direction. In the y direction, I have ND and then my normal force and my weight. So I can actually solve ND now. And again, this is going to be true regardless of what happens with friction. So I know the normal force at D is 525, okay, which is equivalent to the 133 plus the weight of the spool, mg of the spool. Okay, and again, that normal force is true regardless of friction. Okay, now I have the moments. I'm going to sum the moments about point D. Okay, I could have chosen B. I could have chosen many points. I didn't want to choose where P is wrapped up because I want to get P into my equation here. Okay, I chose D, but notice all of the vertical forces go through there. Obviously, the friction at D goes through there. All I'm left with is P and FB. So I have 0.4 meters times FB and 0.2 meters times P in the negative direction. Okay, so at this point, I really only have 2 equations left, this top equation and bottom equation. Okay, however, I've got 3 unknowns. I have P, FB, and FD. So I don't have enough equations to solve the problem. I've already solved my normal forces, okay, but I've only got these 2 equations left with 3 unknowns, so I'm going to have to make an assumption. The assumption I'm going to make is that the spool slips at B. So basically it slides up here, basically sticks to the ground, and it rolls on the ground. Okay. The other assumption I could have made is that it rolled up here and slipped at D. Okay. So it's got to slip one place or the other. Okay, and it effectively rolls on the other one. So I'll assume, again, that it's going to slip at B. Therefore, I'm going to set the friction force to its maximum friction force, which is mu Sn, which is 0.4 for the friction force at B times 133. So again, this friction force assumption is an assumption. I assume that it's slipping at B, so I set the friction at B to be the maximum. Anything more than that, the thing slips. So I'm at that instant right before it starts slipping. Okay. So when I get that, I can go here and I can solve for P. Call P 107. That's solving the moment equation. Plugging 107 here, and my assumption about FB, which is 0.4 times 133, I find that the friction force at D is actually 53.3 newtons. Okay. Now, I'm not done, okay, because again, I've made this assumption. I have to prove the assumption. So what I need to do is make sure that this friction force is not too large. Make sure that it actually can hold at D. So I need to find my maximum friction force at D, which is mu s times n, okay, which is 0.2 times 525, which is 105. 53 is definitely less than 105. Therefore, this assumption is true. Okay, that friction force can happen. Okay, because it could be up to 105. If it's only at 53, I'm a-okay. So the assumption I made is correct. If this friction force had been bigger than 105, my assumption would have been incorrect, and I would have had to set the maximum friction force at D to mu Sn, and then resolve for P. Okay. But since my friction is less than the max at D, everything's fine. My assumption's correct. 107 is the answer to get this to move, and it slips at B and rolls at D.